All right, thanks so much for coming to our session. I am here on behalf of Morgan Windsor, who is a PhD student who led all of this fantastic research. Today I'll be presenting his work on forward prediction of target localization failure through pose estimation artifact modeling. So to introduce, I guess, the context and the motivation for this work, I want to run you through two choice scenarios. If you've seen some of my talks earlier this week, you will have seen the first scenario, but you will not have seen the second scenario, which is an improvement on the first scenario. So the first scenario is knowing when you don't know. So you're picking a positioning system for a surgical robot or an autonomous vehicle, any robot doing something that is absolutely critical. System 1 works 99.9% of the time, but it doesn't have any sort of self-diagnosis capability. It doesn't know when it's not working. System 2 works 99% of the time, so it's not quite so good, but of the remaining time when it's not working, it realizes or knows that it's not working 99% of that remaining time. So if you're doing something that is life and death, literally, which surgical robotics could be, using System 1, you'll be acting on incorrect positional information unknowingly around 0.1% of the time. Using System 2, even though it's only 99%, because it has this introspection ability, that drops to around 0.01%. So it's a much superior system from a safety and reliability perspective. It's not very easy to create, and we've been spending the last few years working on creating systems that enable this for robots in autonomous vehicle contexts and surgical robotics contexts. But the second scenario sort of points to one of the practical problems, even if you're able to develop one of these systems, and this is one of the things that we realized along the way. We've created, and many others have created, systems that predict when your current localization estimate or whatever task your robot doing is likely to be incorrect. System 2, the alternative here, is one that does everything that System 1 does, but additionally it's able to predict forward in time and forward in space when it expects its localization system to fail in the future. This one's an easier one to make the choice. System 1 is great. It will help you detect when you're currently failing or when you have failed. Sometimes that will be too late. The damage will have already been done. System 2 is the holy grail because you can look ahead and predict or anticipate problems you're going to have, and you can act early enough in time and space in order to make the key decisions that you need to make. And that's what this work is all about. The context here, this could apply to a lot of contexts, but we were doing it in the context of total shoulder arthroplasty. This is a joint replacement surgery. It's one of the fastest growing surgeries in the world where you fix a problematic shoulder joint with a surgical procedure. It's because we're living longer, we're being active later in life, so it's a good thing that this procedure is around, but it is also a challenging procedure to carry out. One of the problems with it is you often have to have what is called a revision surgery. Revision rate in Australia, my country, was about 8% a couple of years ago. What this means is that the initial shoulder replacement surgery did not go successfully enough, and you need to go back and do a second or subsequent surgery. And surgery is a traumatic process. You don't want to have to do that if you don't need to. Some of the common problems are loosening in the joints and the bone around the operation, joint instability, and a number of other errors. And these result primarily, or often are linked to implant positioning errors. So errors in how you've positioned and orientated the implant that you put into the shoulder. Around 70% or just under 70% of implants were not sufficiently accurately positioned according to one study. That's a pretty big percentage. This is a sort of task robots are born theoretically to do, a repeatable, highly precise task, and that's what we've been investigating. Apologies, there's a little bit of surgical imagery, but basically part of the surgery involves drilling into the bone, placing a guide wire, and that guide wire is what guides the rest of the surgery. And if you don't place that wire at exactly the right location and orientation, you are increasing the chances of an unsatisfactory surgery outcome. So this is a mock-up in our lab. I'll spare you the more gory details, but you can see the holes that have been pre-drilled. You can see a mock-up of the wire, and you can see it being placed in and out of this hole, just to give you a bit of a visual of what we're trying to do. Of course, people have looked at robots. Robots are heavily used in other areas like hip and knee surgery. Shoulder surgery is the next frontier for robotic assistance in surgical operations. And there isn't a lot of evidence about, or experienced yet with their viability. It's a relatively new field. The fundamental problem is a 6 degree of freedom rigid object pose estimation problem. You're trying to position the surgical tool point relative to a fairly rigid bit of bone. You can't see much of the bone. There's lots of other things making it very visually, perceptually difficult. Traditionally, this task is solved with artificial visual markers, which does work well, but it requires extra time, extra infrastructure. Ideally, you could do this without having to actually artificially install these markers. One of the other things is you need your robot system to know when it doesn't know what it's doing. A surgeon watching this robot doing its thing is not necessarily going to be able to observe the errors or detect the errors that could mean the difference between a really successful surgery and an unsuccessful one. And so the system really needs to have a self-assessment or introspective capability. So the key idea here is in 3 parts. We have a localization pipeline. This is the thing that is running all of the time, that is telling the robot where its tool point is. We have a localization prediction model. This is a model that we train that it learns to predict when the localization pipeline is likely to fail now and into the future. And these systems are used in 2 different ways, a long-range predictor and a next step predictor, to predict forward in space and time whether the localization system is likely to fail, so you can make decisions early enough in order to react to those situations. Some simple basics for how we do this. We construct, using a stereo approach and 2 images, a reconstruction of the target part of the bone that we're working with. We reconstruct the scene as a sparse point cloud of key point features, and we manually at this stage trim that point cloud to only correspond to features on the actual target of interest. The pose estimation pipeline is very simple and straightforward. We're matching the observed key point features from the current camera image against the features stored in the model that we've reconstructed. There's a 2D to 3D correspondence, a list of correspondences, and we do pose estimation using PNP, so random PNP ransack. The key here is we need to find a proxy somewhere in this system that allows us to predict whether performance is going to be good or going to be bad. And there's a lot more detail in the paper about this, but basically, to cut to the chase, we found, not surprisingly, that the number of inliers reported by the ransack loop was highly predictive of pose estimation error. And just to clarify one detail, theoretically you can do pose estimation with 3 inliers, and in some very specific cases I think you can do it with 2. We're observing failure at much higher numbers of inliers, so this is at a larger number of inliers that we're detecting and modeling this failure point. So the aim was to fit a model to predict the inlier count based on the angle of the trajectory as the robot moves through the surgical task. And we used RMSE error to evaluate how well our predictors were doing. We tried a whole bunch of different systems, and again, to cut to the chase, we found that the exponentially modified Gaussian probability density function, or for short, EMG, PDF, was the best. We did use an MLP and a number of other approaches, but some of these needed a lot of nuancing and finessing to actually get them to perform well. So we ended up using this approach. We had 2 predictors. We had a predictor which would take the initial part of the trajectory of the robot and then predict forward in time and predict how far that robot's going to be able to move before its localization system fails. And we had a next best step system which was continually retraining itself and was only predicting whether the next step was going to be fatal for the localization system. And we ran both of these in parallel. One of the things that's important to note is we had this model that predicted the number of inliers forward in time. But inliers are not the actual thing we're after. Inliers are our proxy for predicting whether the localization system is going to work. So there is a threshold for the number of inliers below which we consider the localization performance to likely be poor. And that is a user-defined setting because you can set it based on your risk appetite. You might set a much higher threshold if you want to minimize the chances you're going to stray into a bad localization zone. Experimental methodology, we were using a Franco-Amica arm. We had 21 data sets, I think 4 or 5 different targets, not just bones. We tried some other target objects. And the 2 metrics we were measuring are safe path length, how far the robot predicted it could move before it would get in trouble, and incursion rate, how often the robot moved into a zone unknowingly where its localization system did indeed start to fail and struggle. So these are axes on the x-axis that show how far the robot moved, and on the y-axis is the incursion rate. You want this to be 0. This is when the robot accidentally moved into a bad zone. And you can see that our system is able to stay in the 0 incursion rate longer than some of the comparison systems. And we have 2 different thresholds, 2 different levels of required precision, which would vary depending on this particular task you're performing during surgery. This is another experimental result which shows the predicted safe path. So this is the number of degrees of path or movement through an arc that the robot was predicted to be able to move safely in red. And blue was when we actually pushed the robot to failure, how far it got before it strayed into one of these bad localization zones. What's really nice about this is that the red graph is always less than the blue bars, so we never had an incursion, we never accidentally overstretched and went into a bad localization zone. But at the same time, it's not being ultra conservative. It's predicting up to or pretty close to the actual safe zone in most of these cases, which means it's not being unnecessarily conservative. So obviously a lot of parts of this system are quite simplistic, but it was the integration of all of them together that made it work. There are a lot of interesting areas for future work. We want to extend this to full 3D trajectories. We want to automate a lot of these calibration and threshold selection processes. We want to investigate integrating it into full surgical processes, including possibly testing with cadavers. And this work is theoretically applicable to all other domains where you have a localization system on a robot or a platform that moves. We're already doing this in autonomous vehicles, but there's a lot of other interesting possibilities. And with that, I'd like to acknowledge Morgan for leading this wonderful work, and thank you for your time.
Thank you.